my report. I use my real lab report, just saying.
Okay, so let's get started on aldol reactions, you guys. Last Thursday we covered, hey, let's make sure we're quiet, you guys. Last Thursday we covered alpha halogenation. We're going to continue on doing enol and enolate chemistry for the rest of this chapter. The aldol reaction is a pretty unique example of enolate chemistry, and it's a pretty simple reaction. In the aldol reaction, what you do is you take an aldehyde or a ketone, and you react it with sodium hydroxide and water. And when you do this, you get a beta hydroxyaldehyde or ketone. So if you guys remember our positioning, you would call this the alpha position. You'd call this the beta position. So the name of this product would be a beta hydroxyaldehyde. What do you guys think we call it, the aldol? Yeah, aldehyde plus alcohol, right? Chemists aren't the most creative people, so we just mush names together sometimes. All right, so let's take a look at this mechanism.
Is it kind of long? I'm just wondering if I should turn my page. I'll just turn it.
It's pretty short, but we'll go through it.
Did you say that works with ketones or is it only alcohol?
It works with ketones or aldehydes, and we'll talk more about the equilibrium here in a second. All right, so let's do the aldehyde example that I've got shown here. What's the name of this aldehyde, the one I have shown in the example above? It's acetaldehyde, right? So it's got the acetyl group and then it's an aldehyde, so it's acetaldehyde. And then when we react this with sodium hydroxide, actually let me change, I'll add the equilibrium arrows next. This will come grab the alpha proton, clamp down, and kick up electrons. And it will give you your, whoop. So let's fill it in here in a second. I just want to make sure we get our enol first. Will the equilibrium lie on the right or the left?
The charges on the oxygen, which
Is hydroxide a very strong base?
yes.
No, not really. Not in terms of deprotonating and enol. So if you think about the equilibrium here, the equilibrium is going to be almost all starting material, but a little bit of your enol, or in this case, your enolate. And then we said that the enolate is in equilibrium, or sorry, has a resonance structure where it's got a negative charge on both the carbon and the oxygen. So even though most of it's staying as the aldehyde, there's still a little bit around in solution as the enolate. And now in the next step, let me add in some equilibrium arrows around this corner here. In the next step, we still have excess aldehyde around. So this enol can go and attack excess aldehyde that's floating around in solution and kick up electrons. And then in the last step, we have water around that will protonate your alcohol. So even though we only have a tiny, tiny bit of our enolate in solution, it's enough to drive this addition reaction. It is still under equilibrium conditions, though, which means that you can actually do the reverse reaction for this. And we'll talk about that here in a second. All right, there's a couple key points, though, that I wanted to bring up before we cover the reverse reaction. And the first one is that aldol addition is favored with aldehydes versus ketones.
But didn't you say at the beginning that it could work with the aldehyde also, or maybe ketone also?
Yeah, so when I say it's favored with aldehydes versus ketones, that means that your percent yield of your addition product, meaning the amount present in equilibrium, is much, much higher if you're using an aldehyde.
Okay.
So for example, with an aldehyde doing this reaction, you might get 80% of your beta hydroxyaldehyde. If you use a ketone, you might only get 20%. However, there are tricks we can use to drive equilibrium reactions forward, right? So we can do distillation tricks, and we can do a lot of tricks in order to try to push the equilibrium in one direction. It's just that the reaction is more favorable with the aldehydes in general. Yeah? No? Okay. The question now is, why is it more favored with aldehydes compared to ketones? Does anybody have an idea? Not quite sterics. Aldehydes are more reactive. Why? So if we think about a ketone, it's got two alkyl groups that donate electron density via hyperconjugation. That makes them poor electrophiles compared to aldehydes. So aldehydes are much, much better electrophiles than ketones. And in this case, the reverse reaction can be used to go back to starting materials. And so when we're doing a reaction in reverse, there's a prefix that's commonly used. Does anybody remember what that's called? Yeah, a retro reaction. So in this case, we would do a retro-aldol reaction. Let's take a look at that. And so in this case, what I'll do is I'll show the ketone. So the beta hydroxy ketone in particular. We said that under equilibrium conditions, this isn't very favored because it's a ketone product. So in this case, what ends up happening is your hydroxide will first deprotonate your alcohol in that beta position. And then this next part looks wrong, but it's not. So you guys are going to have to trust me here.
This is one that's going to screw me up and screw me up.
So in this case, we're showing carbon as a leaving group.
Oh, really?
Yeah, I told you guys not to. But as you guys have probably learned from years of chemistry classes, there's always exceptions, right?
Whatever you want. Think about this for you.
All right, why is this a decent leaving group even though it's carbon? Resonance, right? So this is a weird example where you can have carbon act as a leaving group just because it's highly stabilized due to resonance delocalization. With carbons, you don't see it very often outside of this example with the carbon acting as a leaving group. The other example we saw yesterday was the haloform reaction, where if you throw on 3 halogens onto a carbon, you can turn it into a good leaving group. Nitrogens, we'll get back to that when we cover amines. Yeah.
Is that supposed to be a ketone or an aldehyde?
They're both ketones.
Now
Yeah.
after you split them apart, you added a carbon in there.
Oh, shoot. I forgot a methyl group. Thank you. Sorry, guys. So when it kicks off, you get 2 ketones. And then in this next step, you just protonate your enolate. And you can get your retro aldol product. So in this case, taking acetone and sodium hydroxide doesn't yield very much of your beta hydroxy ketone. In fact, it'll primarily stay at the aldehyde, or sorry, your acetone side. So retro aldol reactions are sometimes seen synthetically, but not very often. I just wanted to show you guys the forward and reverse mechanism. The important thing to remember is these are under equilibrium conditions. All right, so what I wanted to do is do some practice problems, see if we can rationalize what the product might look like. And the example I have for you guys is an aldehyde, so this will favor the Aldol Addition product. And we'll react this with sodium hydroxide. So I'll give you guys a minute to try to problem solve your way through this mechanism. I'll show you guys one pet peeve of mine too that I see pretty often in exams. Is students will say, oh, there's a hydrogen right there. Is that acceptable? No, aldehydes are not acidic, not at all, compared to the alpha position. Well, it's a good thing we're doing it now and getting it out of the way so it doesn't go on an exam. So instead we want to go to the alpha position. And we'll put electrons on the alpha carbon. So I'm just going to the enolate with a negative charge on the carbon because we know that's the enolate that's doing the dirty work here. All right, and then in the next step, we're going to have this react with another equivalent of aldehyde. And in this case, I'm going to actually draw the aldehyde a different color so we can kind of see what's going on here a bit better. Okay, so the nucleophile will add into our aldehyde. So in this case, we've got a oxygen with the negative charge. We've got a hydrogen. Oh, let me clean this up a bit. Let's see. There we go. And then what's our last step here? Protonate, right? So the oxygen with the negative charge will come grab its proton. Oh, I forgot my hydrogen there. And the oxygen that was a part of the other aldehyde is now in the beta position. And we end up with our final product. So sometimes color coding these can make it a little bit easier if you are confusing what's adding to what. Also, it's a good way to keep track of carbons too. You want to make sure you're not gaining or losing a carbon on accident. Am I gaining or losing a carbon? No, I'm not. All right. See, even for me, I sometimes look at these and I'm like, yes, okay. So let's do another practice one. This time, what I want you to do is provide the starting materials. So we're going to do retrosynthesis. So what starting material or starting materials would we need here? Well, I'll show you guys the easy trick I do. If we look up here, we made a bond between the alpha and a new beta position, right? So we called this a beta hydroxyketone. That's where the new bond was made. If we look here, we've got alpha and beta. So we could say, all right, the new bond had to be made there. So what do you guys think the product would be?
Something I don't want to name.
Let's think about how to name it too. It'd be an aldehyde, so the suffix would be what? Al. And then we've got a phenyl group coming off of what position? 3. So it'd be 3-phenyl propanol, right? So our aldehyde that we need in this aldol reaction would be this. Do we need any other aldehyde? It just reacts with itself, right? It's acting as its own nucleophile and its own electrophile. So in this case, all we need is sodium hydroxide in order for this reaction to work. So oftentimes you can go from a relatively simple looking starting material to a relatively complicated product very quickly with these aldol reactions. All right, let's look at another one. But this is a slightly different reaction. This is called the Aldol Condensation. When you think of condensation, what do you think of? Water, right? So with an aldol condensation reaction, you're creating water in this reaction. So let's take an example here. And let's go through the aldol addition all the way through the condensation. So the example we had was if you've got acetaldehyde and hydroxide, you can deprotonate your alpha position. And then it will attack itself, or another equivalent molecule of acetaldehyde. And then in the next step, we just protonate, right? And we get to our beta hydroxyaldehyde. All right, so this is just our normal aldol addition. But if you look at our product, we still have alpha protons on there, right? So in equilibrium, we could deprotonate some more of those alpha protons. And again, I'm going to show you guys something that looks kind of wrong, but it's not. So this hydroxide can come, grab one of these alpha protons, clamp down, and kick off hydroxide.
And then it's going to grab another proton.
Well, let's take a look at this. Why would hydroxide in this case act as a leaving group? Normally hydroxide's not a good leaving group. Water is a good leaving group, but hydroxide's not.
Because it's more
Yeah, there's already hydroxide floating around, so we're already under basic conditions. But what's special about our aldehyde now? It's conjugated, right? We said that conjugated molecules are surprisingly stable. So in this case, you can actually use the product's thermodynamic stability in order to drive it. So this is called an alpha beta unsaturated aldehyde. Okay, the other thing that people often wonder about is they say, well, what was that?
I think it's spelled saturated.
Oh, thank you. Oh my goodness.
He doesn't have spell check when
Yeah, I don't have the little squiggly red line to remind me when I'm being dumb. All right, so if we look at that, why are we getting our trans product primarily and not our cis product? Sterics, right? So if we look at this one, we would say that this is minor, and this one is major. And primarily, this is due to sterics, right? If we look at our cis product, we run into this steric clash between the methyl group on our alkene and the oxygen. So in this case, the major product that we'll get is our alpha beta unsaturated aldehyde. So let's kind of make a little commentary over to the side. It forms a thermodynamically stable alpha beta unsaturated, not unsaturated, ketone or aldehyde. Okay, so if we're trying to go to our thermodynamically stable product, what conditions should we use? So we're trying to go to our thermodynamic product. Heat, right? So if you guys remember going back to our kinetic versus thermodynamic product, you can favor formation of a thermodynamic product by applying a lot of heat. So in this case, the reaction is favored by heat, or favored at high temps. All right, so let's kind of look at our summary of what's going on here, because this is something that is a little bit confusing, because people say, well, aren't these really the same reactions? And the answer is yes, they are. They're just under different conditions. So if we have two aldehydes, we can react them using sodium hydroxide to get to our beta hydroxyketone. And then this beta hydroxyketone, we can react to get to our alpha beta unsaturated aldehyde. So if we take these two reagents and react them with sodium hydroxide, we get aldol addition. And this is typically done at lower temps. But if we want to just skip the aldol addition, we can do the aldol condensation. And this requires higher temps. And it's important to remember, too, that we kick off hydroxide that ultimately gets converted into water in this reaction. So you can control whether or not you stop at the beta hydroxyketone or aldehyde, or you can try to push the reaction to the alpha beta unsaturated ketone or aldehyde by controlling your reaction temperature. All right, so let's take a look at an example here.
So the only difference between condensation and dehydration is that one of hydroxy is leaving, the other's water.
Yeah, condensation is just referred to any reaction where water is a byproduct. So in this case, we call it the Aldol condensation because water is a byproduct. Dehydration, water is a byproduct too. Yeah. All right, so let's take an example here. What's this ketone called? Acetophenone. I hope you guys know that one from your project. All right, so we've got sodium hydroxide, hydrogen peroxide, or not hydrogen peroxide, water, and high temps. So let's try to work through this one. What's the first step going to be?
We're gonna grab and put protons.
Okay. Do we have an alpha proton on either side?
No, just one.
Just the right side. This is another common mistake I see people do, is they say, oh, I'll grab that alpha proton.
That's not alpha.
And then it makes me really sad on the inside because you've drawn a Texas carbon. So in this case, we cannot deprotonate on a position without alpha protons. We can only grab a proton on an alpha carbon. So in this case, I'll just draw a hydroxide coming, grabbing that proton. We'll clamp down. All right, so now we've got our enolate.
Oh,
And then in the next step, it can react with the aldehyde.
why doesn't it automatically wanna like do resonance when you push that up?
I mean, you can draw either resonance structure, but the resonance structure with the negative charge on the carbon is what participates in the next step.
Okay.
So we can go ahead and push electrons up. And then in the next step, we've got water around. So this alcohol can come grab a proton. And what's the next step going to be? Yeah. We'll grab another alpha proton and then kick off what?
Hydroxide.
Yeah, kick off hydroxide. So in this case, we'll draw this. Let me draw my alpha protons too so we can clearly see that we're grabbing them. Okay, why is this reaction very favorable?
Hella resonance.
Yeah, it's got a huge amount of conjugation going on in it, right? So oftentimes you see aldol condensations when you form a product that has a large amount of conjugation. Yeah, I don't think hella is the scientific word, but high conjugation.
I like Ian's technical terms better.
Yeah, it's more.
Mine's more descriptive.
Yeah, I guess it's more descriptive. So in this case, the more conjugation you have, the more favored these products tend to be. Yep. So remember, in this first step, I have it drawn as a one-way arrow, but we said that the reaction actually isn't that favorable, which means that most of your product will remain as the aldehyde. So even if you only have 1% of your enol around and 99% of this, that 1% will just add in to the remaining 99% of your aldehyde.
So that's an aldehyde as well.
Oh, no, sorry, ketone. Yeah, so in this case, we'll work with the ketone simply because your final product is so thermodynamically favorable.
So since that product is so stable, even if you didn't have that much heat, would it still go to that?
Yeah, oftentimes the amount of heat you apply has to do with the activation energy to get to your transition state, and that can vary depending on the amount of conjugation. Typically, the highly conjugated molecules have a lower activation energy in order to get there.
Okay.
Yeah. All right, so now I've got a troubleshooting problem for you guys. All right, I'm going to color code them for you too. So I've got my red aldehyde, and I've got a blue aldehyde. No, just red and blue. And we're going to add in sodium hydroxide here. What product would we get out of this? This is kind of complicated, right? So let's take a look. We've got alpha protons here, right? But we also have alpha protons here. So we can pick and choose which alpha protons we want to deprotonate. So let's just pick one. So for this first example, let's say we're using the red one and it attacks itself. If we do that, we end up crossing two of our red aldehydes together, right? So we deprotonated that green position on the red one. So that's one product we could get. Or we could take the green position and deprotonate that off the blue one. And if we do that, we'll get a different product. And if we do this, the product looks slightly different. Right, so we could couple two red aldehydes together or two blue aldehydes together. What's our other option?
Mix them.
Yeah, we could mix them. And in this case, it does matter which one is the enolate, right? So let's have the red one be the enolate first. If we do that, that means it'll still react with the blue aldehyde. Right? So it's slightly different. It's really similar to the one on the top, but we have an extra methyl group off the end. Or we could have one where the blue aldehyde acts as the enolate. And if we were to do this, then we would get a different product. And this is pretty problematic, right? And what these are called are cross Aldol reactions, not condensations. Yeah, let's go back to that here in a second. All right, so in this case, do you think we're being stereospecific when we do these reactions? Well, let's think about it this way. When we have a carbanion, does it have stereochemistry? No, we don't have stereochemistry when we have a negative charge in a p orbital. So in this case, these aren't stereospecific. And as a matter of fact, this isn't even regio-specific. You'll get a mixture of all 4 of these products out, which is a big problem for doing a lot of these aldol reactions, especially if you're trying to use 2 different aldehydes. Does it have what? Oh, yes, thank you. I was looking at the red one. Sorry, there should be a hydrogen here, and there should be a hydrogen here. Sorry, I was moving too fast. They should all be beta hydroxy aldehydes. Sorry about that. So you run into this problem of getting 4 different products, and it can be pretty hard to control. But there are a few tricks that chemists use to try to control cross-aldol reactions. Yep, there's always tricks.
Oh, man. What's like the highest, craziest, deepest chemistry level there is? Where do you max out at?
I don't think there is a maxing out. Even the best chemists spend their whole career learning new reactions. All right, the first trick is use only one aldehyde. Or ketone. Right? If you only have one aldehyde or one ketone, you're only going to get one product. You only run into this when you use 2 different aldehydes or ketones. The other one is that you drip your first aldehyde or ketone into LDA. What does LDA stand for? Okay, and why do we use LDA? Because it's ginormous and it's a crazy strong base, right? So we're dropping our aldehyde or ketone into a really, really strong base rather than hydroxide. What will this do? This will cause all of your aldehyde or ketone to become an enolate. There won't be an equilibrium if you're using a crazy strong base. So if you do this, you don't have any remaining aldehyde or ketone lingering around. At that point, all you have is enolate. 0% aldehyde, 0% ketone. All right, now that you've formed your enolate, then you can add in your second aldehyde or ketone. So in this case, you're making your enolate exclusively in the first step, and then in your second step, you're adding in your second aldehyde or ketone. This is not a shake and bake, pour it all in and mix it reaction. This actually has to have very careful order of addition. So that's one key thing I want you guys to take away from this, is that order of addition is key. All right, I've got another question for you guys. Why don't we drip the LDA into our aldehyde in the first step?
It will make it easier from some of your products that will react with the other chemicals.
Exactly. So in this first step, if you take LDA and you drip it into a sea of aldehyde, it'll form an enolate with maybe 1%, right? Assuming we haven't added all of our LDA, and then that will react with your remaining aldehyde, and so you'll get an aldol condensation with the aldehyde itself. But if you do it in the reverse order and add the aldehyde to a sea of LDA, then you'll exclusively get enolate before it has a chance to add into itself. So in this case, the order of addition, even for that first step, does matter quite a bit. So you don't want to add your LDA to your aldehyde. You want to add your aldehyde to your LDA. That'll make a much, much cleaner product. All right, let's take a look at some examples here. Let's do just a generic one. And I'll use one as a blue aldehyde. And we're going to react this with sodium hydroxide and heat. What's one beneficial thing about this reaction compared to the previous example where we got 4 products?
Only one starting material with alpha.
Yeah, exactly. So in this case, only one starting material has alpha protons. So in this case, we're not really running into the problem of our mixed aldol, because we only have one position where there are alpha protons available. So in this case, we'll just show deprotonation of one of these. And we have a negative charge. And then we still have benzaldehyde around. So the benzaldehyde can act as an electrophile, and our enolate will add in. And then we end up with our, sorry, there should be a negative charge on our alkoxide. And then what's our next step? I kind of skipped it before. Protonate. Oh, shoot, that should be an alcohol. All right, so now we've got our beta hydroxyaldehyde. What would our next step be?
You can do it again.
Yeah, exactly. We can drive the elimination. So if we look over here, we've still got an alpha proton. So this hydroxide can come, grab that alpha proton, clamp down, and kick off our hydroxide. Oh, let me make sure this double bond's clear. There we go. And we can end up with our alpha beta unsaturated aldehyde product. In this case, it's impossible to stop at the beta hydroxyaldehyde. And why do you think that is? Why do you think we can't isolate that?
Because it wants to be conjugated.
Yeah, it wants to be conjugated, right? So if we look at this, we can say this is highly conjugated, which really drives the reaction forward. This is thermodynamically very downhill. All right, let's do one last practice one before we leave, but this time do retrosynthesis rather than forward mechanism. And this time I want you guys to figure out what aldehydes or ketones you need for your starting material. And when we do retrosynthesis with these, what's a good starting point? Yeah, look at the alpha and beta position, and you know that that's the first bond being cut. So what two products would we need? Yep, butanal or butanaldehyde. What would our next one be? It'd be 3-pentanone, right? So the question is, what order would we want these to be added? And like I said, the order matters a lot. So let's say we start with our 3-pentanone. What would our first step be? So not NaOH. NaOH would cause it to do an aldol reaction with itself. LDA, right? So we're going to add this to a sea of LDA, make sure we exclusively get our enolate. So that'll be step one. Oh. And then the next step, once we've got our enolate, will be what? Nope, we've already made our enolate. We don't need to add more base. Yeah, just add the other aldehyde, right? So in this case, once we have our enolate, we can just throw in our next aldehyde, which the enolate will add into. And then in the last step, we can add water. So in this case, we're not doing this under high temperature conditions. So we'll end up with a beta hydroxy ketone.
Would you get something different if you reversed it?
If you use the butanaldehyde as your starting material, it'd be this slightly different product. You'd have a double bond in the other position. So you do need to choose your reagents wisely. So in this case, you can tell that the attack occurred at the alpha position. So in this case, the deprotonation had to occur from that starting position. All right, so the problem of the day is looking at a reaction that we're going to cover tomorrow, but see if you can do it on your own without actually opening up your textbook and looking at the mechanism in the next part. I think it's fairly intuitive.
Yeah, I'll do that, Dr. Angel.